Hi everyone, it's Wednesday, which means it's another Chem Help ASAP live stream. This week, again, we are going to be focusing on AP Chemistry exam, either questions from the exam or questions like the exam, because obviously there are a limited number of questions from the exam that we can use. Also, what I want to say, I'm trying to remember to say at the beginning is these live streams are not just for AP chemistry students, they're for any students. So if you are maybe in an intro level course or maybe you're taking college level chemistry, just let me know what topics you're struggling with, where you need help, what you would like to see done in the live stream. However, I know that the AP students are looking at the exam. It's coming up close. I think the exam is May 1st. So hopefully this can help you. Also, I am running an AP chemistry exam review course. If you want more intensive review, lots of problems, lots of help, lots of finding those knowledge gaps that I know students have, and then filling those knowledge gaps so that you can do well on the AP exam. Okay. Oh, good. I was just getting ready to ask you, OG Benchmarks, if my audio was good. So with all of that being said, we are going to jump into electrochemistry today. So all of these problems are going to be doing electrochemistry. Just like last week, we did equilibrium. Again, if you have a request, let me know. I'll try to keep an eye on the chat to see if you've got questions coming in. Okay. So let's go ahead and start our first question. All right, so this first question is actually part of what's going to be a series of questions, and that'll make sense once we get a little farther in. But this one says, write the balanced redox reaction for each of the following. So we've got A through E, and we're going to determine Ecell, and we're going to state whether the reaction is thermodynamically favored or not. So the real crux of this problem is, of course, calculating Ecell. Now, I do have on the next page, because we're going to need this, I do have a list of our half reactions that we are going to be using. Now, on the AP exam, they will also have to either give you a table with half reactions, or they will have to give you the voltage of the half reaction in the problem. So this is a table of all of the half reactions that we are going to need. So it's going to be a little bit of flipping back and forth. Okay, with that being said, let's go ahead and start on question A. So question A says the single displacement of copper 2 by zinc metal. So the first thing that we're going to need is we're going to need a redox equation, a balanced redox equation to know what's going on here. So there are really kind of two ways to do this. So for part A, for reaction A and reaction B, I'll kind of do it one way, and then for reaction C, I'll show you a different way to do it. So for A, the displacement of copper 2 by zinc metal, I'm actually going to put in what are my spectator ions. So I have, this is for A. Oops, that is a really bad Z. We have zinc metal, so that's our solid. It's replacing our copper 2. So instead of just writing copper 2, I'm going to give it an anion. Now, you can make the anion whatever you want. I'm just going to go ahead and give it a nitrate anion. You could do chloride. You can do anything. Again, this is a spectator ion. But this is just so the reaction looks a little bit more like what you're expecting it to look like. And of course, now we've got copper solid. So sorry, these are both aqueous here. Okay, so you don't want to do a spectator ion that's going to cause a precipitate. But you can see here, you're going to have your charge on your copper is going to be 2 plus, and your charge on your zinc here is going to be 2 plus. So sometimes doing it like this can help you figure out what's going on in the reaction. But again, I'll show you a different way for part C as well. Just do the way that makes the most sense to you. All right, so now that I have a balanced chemical equation, I want to pull apart my two half reactions. So my two half reactions are my copper, which is being reduced to copper metal. So that's a solid that's got a state of 0 there. And I've got my zinc, which is starting as a solid. So sorry, this should also be written as aqueous. And it is being oxidized 2 plus 2E minus. All right, and that is also aqueous. Now to calculate Ecell, we have really a very simple equation where Ecell is equal to our E at the cathode minus our E at the anode. So we're going to be using this equation just over and over and over again. So the trick for this equation right here is obviously correctly identifying your cathode and anode. And there is a very popular way to remember that, and that is red cat and then an ox. Or sometimes you'll see it as an ox, red cat. But what this does is it means you've got reduction at the cathode. So that is your red cat. And an ox is anode is oxidation. So I'll draw an arrow over here. So that is a way to remember what's happening at which anode, and so which number to put in for E cathode and E anode as well. So for our reactions right here, we obviously have our copper is undergoing reduction because the electrons are on the left-hand side. And so this is going to be our cathode. Our zinc is undergoing oxidation. Again, electrons are on the right-hand side, so this is our anode. So now we know what numbers to put in which places. So for our cathode, we need our half reaction for copper 2 going to copper 0. So we're going to go take a look at our potentials here. Copper 2, copper 2, copper 2. Where are you? Here you go. So here is our reaction. So that is our half reaction. Here is our voltage right here. So let me go back, and we're just going to plug these numbers in. So our E cathode is 0.34 volts minus our E anode. Again, our anode is our oxidation. This is our zinc. Now, when you look back at your reduction potentials, these are all written as reductions. So our zinc obviously is an oxidation, so it's written with the electrons on this side. So you're looking for the reverse reaction of this when you're trying to find your numbers. So blurb, 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 blurb. So here, you can see here is our zinc down here. So you can see how it's reversed, because when you're given reduction potentials, I mean, that's why we call them reduction potentials. They're always going to be written as reductions. But here is our number right here. So now I'm just plugging that in. That was a negative, what was that, 76 volts. And so our E cell is simply 1.10 volts. And the other thing that we have to determine is this reaction thermodynamically favored? Well, we have a positive E cell. Oops. That was terribly written. Positive E cell. So that means, yes, we are thermodynamically favored. Okay, so at least the last part's easy to identify. So this is what we're going to do for B, C, D, and E. It's the same thing. So we want to make sure we get our half reactions, and we want to identify which is our reduction happening at our cathode and our oxidation happening at our anode, so that we can get the right numbers into our E cell calculation. Okay, so the single displacement of H plus by iron forming iron 2. So I'm going to have to go to the next page. And let's go ahead and get this down. So we have the displacement of iron. So that's solid. And it's reacting with an acid. So if I come back here, so it's displacing this H plus. So again, I'm going to write this as kind of a regular balanced chemical equation, and then we'll convert it to our half reactions. So we know that that's going to be an acid. So let's call that hydrochloric acid. You can call it whatever you want, whatever acid you want. That's just kind of the first one that came to mind. So again, we've got a single replacement reaction. And what helps in this case, sorry, these are aqueous, and then this is a gas, is you can look at this equation and hopefully you see that it is not balanced. So this is not a balanced chemical equation. This is a chemical equation. So I find it easier to balance when it's written like this rather than necessarily balance when it's written as half reactions. But you can do either way. It really just depends on what makes the most sense to you. And this is pretty easy to balance here. So now let's get our two half reactions going. So again, we're reacting our 2H plus. Again, so this 2 is coming from this balanced chemical equation right here. That's going to be 2 electrons, and that's giving us our hydrogen gas over here. And then we've got our iron, which is starting out in solid, and it's going to iron 2 plus, and that is also 2 electrons. Okay. So these are my half reactions that I have pulled from my balanced chemical equation. So my hydrogen, of course, is undergoing reduction. So this is the cathode. And my iron is undergoing oxidation. So this is my anode. And let's go ahead and get our equation for Ecell. So Ecell is equal to E cathode, minus E anode. And now I need to get my voltages for each of these half reactions. So let's start with my hydrogen reduction. Going back to my table. Hi, okay. Yep, hydrogen reduction. So you can see this is 0. So this is the standard electrode that we measure all of the other half reactions by. So it's not surprising that it is 0. That is called the SHE standard electrode. But that's fine. We can still, we can absolutely just plug 0 in here. So that is 0 volts. So don't panic if you see a 0. That's a valid number. It's a valid value to put into this equation. And then I need my E of my anode. Again, remember, you're looking for the reverse of this reaction because this is an oxidation. So I'm looking for my iron 2 to be reduced to my iron. So going back to my table. Here we go. Here's my iron, and I've got a reduction potential of negative 0.44 volts. So my E cell is going to be 0.44 volts. And because I have a positive E cell, this is another favored reaction. Okay. So we've got C, D, and E to do as well. So the point of doing all of these repetitions is, one, you can see slight variations in the questions. And also the more repetition you're going to get, the more comfortable you're going to get doing these calculations. You're just laying down those neural pathways as you get more practice in. Okay, so I have to go back to our question. Sorry, there's just a lot of switching back and forth here. So I'm on to C, the reduction of 10,4 to 10,2 by the oxidation of iron 2 to iron 3. Okay, so we're going 10,4 on the reactant side, 10,2 on the product side. Iron 2 on the reactant side, and then iron 3 on the product side. So instead of writing a chemical equation out like this, for this one, I'm going to show you the ions. Again, you can do it either way. It just depends on, here I'm going to give myself a little space, which way makes the most sense to you. All right, so we've got our 10,4 and our iron 2, and it's going to 10,2 and iron 3 plus. All right, now what might not be so obvious here is while our atoms are balanced, our charges are not balanced. So this is not a balanced chemical equation, or I should say it's not completely balanced. So when you have a balanced chemical equation, not only are your atoms balanced, but your charges are balanced as well. So we need to balance our charges here, but thankfully this is really not very difficult. I'm just going to put a 2 here and here. So what I've done is this is now a total charge of +4, which is 8. This is +2 +6, which is also 8. So it's not that your charges have to be 0 on both sides. They just have to be the same on both sides. And then you have a balanced equation. Okay, so these are redox equations that really you can balance by inspection instead of going through the half reaction method. But we will also go through the half reaction method, but these are pretty easy. Okay, so now that we've balanced our chemical equation, we need to, again, identify our reduction, identify our oxidation, so we can identify our cathode and anode and know what to plug in where. So we've got 10 4 being reduced to 10 2. And balancing the charges is another way that if you're unsure if something's being reduced or oxidized, you just want to make sure that your charges are balanced here. So you can see for this half reaction, I have +4 minus a 2 here, because this is 2 times -1 gives me a +2 on the left-hand side, and I also have a +2 on the right-hand side. So if you're ever unsure which side do I put my electrons on, you want to put your electrons on the side that's going to balance your charges. Okay, so this is our reduction, which means it's happening at the cathode. And our oxidation is our iron. And so this is our oxidation. It is our anode. And now we're ready to plug into Ecell. Just for the sake of space, I'm not going to rewrite this one more time. I'm just going to plug in. So I'm going to piggyback on this equation right here. So what I first need is I need reduction potentials for my reduction for my 10, going from 10.4 to 10.2. Okay, here we go, 0.15, 0.15 volts. And then I need, again, this is going to be backwards, so I want my reduction potential from iron 3 to iron 2. Here we go, iron 3 to iron 2, 0.77. Now, a common question that you get is, this has a 2 in front because we had to balance it. If you remember, we had to balance it up here. But if you go back to my reduction potentials, these do not have 2's in front of here. So sometimes the question is, do you need to multiply your reduction potential by 2? And no, you do not need to multiply it by 2. You can just put it in just as is. Okay, so then we have Ecell is going to equal, for this one, what is that? Negative 0.62 volts. So we have a negative value for Ecell, which means this is not favored thermodynamically. Okay, questions? All right, it looks like either we're very confused or we're not confused at all. So let's keep on going, except I'm going to pop back because we've got to read part D here. Okay, so this one is going to be a little bit more difficult. We have the reduction of dichromate ions to chromium-3. So this is reactant product by manganese +2 to manganese oxide. So reactant product. So we need to get a chemical equation, and we're going to have to balance this redox equation by the half reaction method. I know it feels like a lot, and I'm going to need an extra space here. So extra page. All right, so let's just get our species in the right place on reactant sides and product sides. So we've got dichromate, and manganese, and this is going to chromium and manganese oxide here. All right, so we definitely have redox going on. This is not one that I can balance by inspection because I'm definitely going to have to put waters in here. And again, the easiest way is to balance it in acidic solutions. So let's go ahead and balance this equation. So that then we'll identify reduction and oxidation as well. Now, the problem didn't specify that we have to balance it, but often the case is you have to specify it. It's also going to help you identify your half reactions better if you can see the full half reaction where it's balanced with waters and with acid. So I'm going to pull out my dichromate first. All right, it's going to chromium 3 plus. All right, so the rules here is first we're going to balance everything that's not oxygen and not hydrogen. So I'm going to put a 2 here in front of my chromium 3 plus, and now my chromiums are balanced. Next, I'm going to balance my oxygens with water. So I have 7 oxygens on the reactant side, which means I need 7 waters on the product side. So now my oxygens are balanced. Next, I'm going to balance my hydrogens with H plus. So I'm going over to the reactant side, and I have 14 here. 14 H plus. So now at this point, all of my atoms should be balanced, but my charges are not balanced. So I need to put electrons in such that my charges balance. So what I've got going on here is this is a plus 14 minus 2, so this is overall plus 12. And I've got a plus 6 here because this is 2 times 3, that's plus 6. So I need plus 6 electrons on this side. So this is my balanced half reaction for my dichromate going to my chromium 3. You'll see that the electrons are on the reactant side, on the left-hand side, so this is a reduction, which means this is our cathode. All right, let's go ahead and balance our second one. So this is our manganese 2 plus going to manganese oxide here. Again, the manganese are already balanced, so I'm going to jump straight to adding waters to balance my oxygen. Waters to balance my oxygen. So I need 2 waters on this side. All right, so now I'm going to use H plus to balance my hydrogen atoms. So that is 4 H plus on this side. And now I need to balance my charges by adding electrons. Now, because I have a reduction for my first half reaction, I know I've got to have electrons over here. The question is how many? So I'm going to look at the charges. So on my reactant side, I have plus 2. On my product side, I have plus 4. So if I add 2 electrons, then now my charges are balanced. Okay, so this is my oxidation. This is my anode. So that I know how to put this in. Now, just for time's sake, you can add these 2 half reactions together. You can simplify your waters and you can get your balanced chemical equation, but the problem actually didn't specify that. They just want Ecell. So what I'm going to do is I'm going to find my 2 half reactions and I'm going to calculate my Ecell. So let me go ahead and get this equation in. Minus E at the anode. All right, so first I'm looking for my dichromate. So let me go back to my table. So dichromate, so you can see here's my dichromate. Now, what we could have done, although it's a nice check, is you can see that this half reaction looks exactly like what we wrote down. So depending on how much information is given to you, you could have first gone to your table, found your dichromate, and found your half reaction and use that instead of going through okay, I've got to balance my chromiums, my oxygens, and my hydrogens. You can kind of go either way. It's just which way can you work through faster? Is it faster for you to just go ahead and write it out because you can do that very fast, or is it faster for you to find in the table where the half reaction is? But anyway, here is my voltage. So this is 1.33 volts. And now my anode, again, remember your anode, this is my oxidation. So I'm looking for this half reaction in reverse in my table. And you can see it's right up here, and here's my voltage, 1.23. Okay. Volts. So now I just go ahead and calculate Ecell, and that is 0.10 volts. So my Ecell is positive. So this is favored. All right, we're almost there. I know it's all the repetition. Okay, so this is the last one, and this is going to be the same kind of deal as D. So we have the oxidation of ASO3 to our acid, and the reduction of iodine to iodide. So be careful here. Iodine is your I2, and iodide is your charged ion, your I minus. Okay, so same thing. Whoops. Nope, don't do that on me. Okay, so same thing as up here. First, I'm just going to get all of my species into the right place, and then I'll pull out my half reaction so I can identify my reduction and my oxidation. All right, so we've got ASO3. Remember, your iodine is one of the diatomics, just like hydrogen when it's in its elemental form is H2. Iodine is I2. So that is just something that your AP exam is going to expect you to know. And iodide. Okay, so here are my species in the right place, but I need to pull out my half reactions and I need to balance them. So let's start with our arsenic compounds first. All right, and we're just going to do the same thing that we did before. Again, because we don't have to get the total balanced chemical equation, we're not going to worry about actually adding our two half reactions together and canceling everything out. But you can if you want that extra practice. It's totally fine. Okay, so for this one, I'm going to go... My arsenics are okay. I need a water over here. And then my hydrogens are okay as well. Okay, so now I'm going to go to charge. So this is -3. That's -1. So if I add 2 electrons over here, that gives me my balanced charges. This is my oxidation. This is my anode. All right, so it means my other one must be my reduction. I2. Make sure you balance your atoms as well, and you can see that this definitely needs 2 electrons over here. Okay, so this is my reduction. This is my cathode. Again, to save space, I'm not going to rewrite my whole equation. I'm just going to go ahead and plug some numbers in so I can fit this in. So E for my cathode, I need my iodide here. Let's go back to my table. Here we go, 0.54. 54. And then my anode is my oxidation. Remember, you're looking for the reverse here. Now, the nice thing is my table is pretty small. Here we go, 0.58. So it's easy to find, but potentially on the AP exam, you could be given a very large table. And that's why it might take you a little bit of time to find these reduction potentials. Okay, so my E cell here is really quite small, but it is negative volts. So E cell is negative, which means it is not favored. All right, so that is calculating E cell for all of those half reactions, but we're going to still need these E cells because check out my next question. So this is kind of why I liked this series of questions. So I've got the same reactions here, A through E, but now I'm going to determine the equilibrium constant for each. So I'm still going to take the E cell that I calculated from the first question, and now I'm going to use that to calculate the KEQ for each of these reactions. So again, it just kind of ties everything in, and the AP really loves to do this on especially the free response questions. Okay, so let's first talk about how we get KEQ from E cell. So the AP exam is going to give you this equation as part of your equation pack. RT over NF ln of Q. All right, so it gives you Q, but you actually want KEQ. Now, the great thing about this, so this is the Nernst equation, great thing about this is when equals KEQ, not EQ, when Q equals KEQ, then we can simplify this equation. So we're really just using Ecell because this term here goes to 0. Now, one thing I want to do is I want to simplify all these constants because I don't want to constantly be plugging in RT and F, because RT and F are going to be the same for all these. So of course, R is your universal gas constant. Your temperature is given here. So it's 298, which is 25 degrees C. And of course, you have Faraday's constant, which the AP exam will give you. So the common thing to do at this point is to actually take your natural log of Q and convert that into a log base 10. So this is an equation you will probably recognize. It's a very common one, and that is E cell is equal to 0.0591 over N. So that's your number of electrons that are transferred times log of KEQ. Okay, so this equation is true when Q equals K, when you're at standard conditions, which we're at standard conditions. And this constant up here is basically the, not the N, but the F, the RT over F, and converting this into log. So again, this is probably an equation that you are recognizing. So we're going to use this one to calculate our KEQ for all of these equations. So this calculation is actually going to be a little bit easier than the calculations that we previously did. So let's go ahead and start problem A. So if you remember our E cell, we've already calculated, what was that, 1.10 volts. Our number of electrons is 2. So let me go back and just show this to you for part A here, all the way back here. So here is where we calculated our E cell, again, 1.10 volts. And here is where we transfer 2 electrons. So that is what our value of N is. Okay, keep coming all the way back here. So that is where I get my N equals 2. So you really have to have both of these to be able to calculate your KEQ. But calculating the KEQ is pretty straightforward. So I'm just going to plug into this equation right here. So this is 1.10 volts is equal to 0.0591 divided by 2 log of KEQ. So then you just do your algebra. And you get a KEQ of 1.7 times 10 to the 37th. So it's a pretty big K there. But again, we already knew this was thermodynamically favored too. So having a large K is not that surprising. Okay, and so that's it for the calculation for A. So we're going to do the same calculation for B, C, D, and E. All right, so coming back around here for part B. Our E cell for this one was 0.44 and our N equals 2. Again, let's go back and check so you can trust me with this. So here is is that one part B? I think that one was part B. Yes, I should have labeled these. Okay, this one was part B. So yes, here is our E cell. Again, you can see we're transferring 2 electrons. So that is where our N comes from. So N equals 2. All right, so our, let's not go ahead and write KEQ first. Let's get our equation. So E cell is equal to 0.0591 over N times log of KEQ. So let's plug our numbers in. This is 0.44 volts, 0.0591 over 2. Log KEQ, and when you do your algebra, you get a KEQ of 7.8 times 10 to the 14th. Okay, so you can see, that's not B. So you can see how these are fairly straightforward. Again, once you get the Nernst equation in the form that you can use it, then you're just plugging in what you've already calculated. All right, so for part C, we calculated an E cell of negative 0.62 volts. We also had an N equals 2 here. So I'm just going to, again, plug in here, 0.62 volts is 0.0591 over 2 log KEQ. Do a little algebra, and you're going to get a KEQ of 1.0 times 10 to the negative 21. That's really awful 10. Times 10 to the negative 21. So you'll notice here, which I think is pretty cool. So your KEQ here has been, or for A and B, we've had a positive exponent, but then our Ecell has changed to negative, and look, we get a very negative exponent. We know that this is not thermodynamically favored as well. So this reaction really lies very strongly to the reactant side. Okay, let's go ahead and do D and E over here. So for D, we calculated an Ecell of 1.33 volts. Now for this one, our N equals 6, and I'll show you why. Here. All right. So remember we broke this one up into our two half reactions, but because we didn't need a balanced redox equation in the end, we didn't bother to add them together. But you'll see that here you're transferring 6 electrons and here you're transferring 2. So if you were to create a balanced redox equation, you would have to multiply this one by 3 to make sure that your electrons canceled. So this is where I'm getting my N equals 6 from. So I took a little bit of a shortcut here. Again, that's fine because on the AP exam, you want to move as quickly as you can. So if you can take a shortcut, take a shortcut. But this one I had to at least recognize when I came back for this next part that I didn't transfer 2 electrons because 2 and 6 don't cancel out. But this one had to be multiplied by 3 to make it 6. So your N equals 6 here. So that is something to just be aware of and to look out for. All right. Oops. So let's again plug into our equation. 1.33 volts is equal to 0.0591 over 6 times log of KEQ. Do our algebra. Let me see. I did that calculation. Here it is. 1.4 times 10 to the 10th. Okay, again, very favorable, but we started with a positive Ecell. So we got a question. Yes, please recommend a good... that's an unrelated question. So that's more an organic question. So what you really want is I would say, an organic textbook. Any of your basic organic textbooks. I'd say I'm most familiar with Wade, but there are a lot of textbooks out there. Actually, OG Benchmarks, I know, has more experience with the organic textbooks. So he might be able to respond and offer you a good recommendation for that. Yeah, because finding those isomers can be tough sometimes. Okay, so on to our electrochemistry, which is definitely not finding isomers. So for our Ecell equals, this was the really tiny one, and our N equals 2 again. So if we go back to our equation, so this was our last one right here. Again, you can see that we've got our 2 electrons, that's N equals 2, and here is our calculation of Ecell. So this Ecell was actually almost 0. It was really close. So let's plug in. So we've got a negative is equal to 0.0591 over 2 log KEQ. And so our KEQ is 4.4 times 10 to the negative second. Okay, great. So this one was a little bit easier. Again, you just have to make sure that you're getting the right value for N in your equation, because that's going to obviously give you a different KEQ. So that's kind of the only difficult part, I think, about this is once you have manipulated the Nernst equation such that Q equals KEQ, then you're pretty much set to go. Okay, so we have one more question in this series. We're still working with the same A through E. Again, I like this. It gives us a lot of repetition because ideally, as you're prepping really for any test or exam, you want to be able to do enough problems that you're starting to get bored with them. You're like, We have to calculate KEQ again. This is the same thing. I've done this 5 times now. So that when you go to sit for your exam or you go to sit for your test, you can read the questions and go, oh, I did that a million times. I totally know how to calculate this. That's really what you want, which is by practicing these extra questions and doing the repetition, like having A through E here, is really helpful. So by the time hopefully you hit your calculation for part E, again, you're hopefully at least a little bit bored and you're ready to move on because you've done this so many times. Okay. All right. Oh yeah. Thank you, OG Benchmarks. So yeah, he's going to have good recommendations for you. So for our equations now, we're going to calculate delta G. So we're calculating free energy. So our equation that we're going to use, and this is one that the AP gives you, is negative NF E cell. All right, so we've already calculated E cell. We already know what our N values are because we had to use them previously. So the only new part here is F. This is Faraday's constant. Again, the AP exam will give this to you. So at this point, we're really just plugging and chugging. So let's go ahead and do this for part A. So our delta G is equal to our negative, so our N, so hold on. Let me just specify everything here so that we've got our values. So our E cell for part A was 1.0 volts, our N equals 2. So now let's plug into our equation. So delta G equals negative 2. Faraday's constant, again, this is, and you know what I should really do? I should put in my units. That's 2 moles of electrons times Faraday's constant is 96,485. This is coulombs per moles of electrons. And our E cell is 1.10 volts. So in terms of units here, of course, your moles of electrons cancels and you end up with coulombs, coulombs times volts. So this is going to give you joules. So when you calculate this for delta G, it's going to calculate it in joules, just so you know what the unit is. So this is going to give us negative 2.12 times 10 to the 5th joules. Now you can also convert this to kilojoules. The problem didn't specify, so you can go either way. But depending on maybe what you're going to do next, sometimes kilojoules is helpful to have. So this is what our delta G is for our reaction for A. So let's go ahead and do our reaction for B. I'm going to move this up. Okay, so for B, we calculated an E cell of 0.44 volts. N equals 2 again. So I'm just calculating delta G here. So this is our negative 2 moles of electrons times our Faraday's constant again, 485 coulombs per mole E, and times our E cell volts. And we get a delta G of negative 8.49 times 10 to the fourth joules, or negative 84.9 kilojoules. Again, whichever way you want to go with it. Okay, so on to our next one. So for part C, we had an E cell of negative 0.62 volts, and our N equals 2. So again, I'll write the equation again up here since we've gone to a new page. E cell. So this is negative 2 moles of electrons times Faraday's constant, 45 coulombs per mole E, and times our voltage, negative 0.62 volts. All right, so for our reaction at C, we get a delta G of 1.20 times 10 to the 5th joules, or 120 kilojoules. Okay, all right. Oh, good. We got the links. Okay, so D, I thought I saw some chats going on there. For part D, our E cell is 0.10 volts. Our N, remember our N was 6 for our reaction for part D. So our delta G is -6 mole E times Faraday's constant per mole E times our voltage here. Again, we're just getting lots and lots of repetition. 10 to the 4th joules, or -57.9 kilojoules. Okay, so our last one, again, hopefully by this time that you're getting down to E, you're getting bored and you know exactly what you need to do, and the only issue is writing it down. It's -2 mole E. So remember, if you're doing this question as a free response, though, you want to make sure that you write down all of your steps. So they are particular about seeing all of your steps on the FRQ and seeing all of your units. So even though by the time we hit part E, we're just really tired of writing this down, you want to make sure that you write it down so that you get all of your points for your answer. Now, if you're doing if you're just doing a multiple choice, then of course you can do what you want. And if you need to save time by just plugging in your calculator, then you can absolutely do that. Okay, so that is our delta G for all 5 of our reactions. And again, I really liked that series. So you can see how you can take Ecell and you can use it to find KEQ, and you can also use it to find delta G. And, you know, they throw in things like, is it thermodynamically favored? And they could have done that in any of these pieces, but they decided to do it at the first. So it's just something to keep in mind. Okay, how are we doing on time? We're getting a little bit short. So what I think I'll do is we'll definitely do this one because this is an electroplating question, which I think is really good, but I don't think we're going to get to our sketching out of our electrochemical cell just because we're on a little bit of a time crunch now because it's 10 to 8. So what we've got here is we've got a current with 1.25 amps. How many minutes will be required to deposit 2 grams of copper on a platinum electrode from a copper 2 nitrate solution? And they give us Faraday's constant here. Now we already, you know, the AP exam is already going to give you Faraday's constant, but it's nice to have it right here instead of flipping back and forth. Okay, so let's first just get our redox equation. What is going on here with the copper? So we are plating copper. So we've got a copper 2 nitrate solution. So that is aqueous, and it is plating to copper solid. And so our nitrate here is just a spectator ion. It just hangs out. You can also write this equation if you want to simplify it down to just the redox. You've got copper 2 being reduced to copper solid, or copper 0 here. So you've got an N equals 2 electrons. And we're basically going to treat this problem as a dimensional analysis problem because that is what it is. It is a long dimensional analysis problem, but all you're going to do is you're going to string together your conversion factors so that you can convert from grams of copper to minutes. Now, one thing that we're going to need that's going to be really helpful here, besides Faraday's constant, is to know that 1 amp is equal to 1 coulomb per second, or per 1 second. So that is, while mathematically it's not going to change anything, it'll show you how to make your units work out the way you want them to do. So we're going to start with our 2 grams of copper. So that is how much we want to plate. And we're going to figure out how much time it's going to take. So we've got I'm going to need a lot of space for this one. We've got our 2 grams of copper. Okay, we just tried Wade. Oh, okay. Yeah. So based, hopefully you can get that, that playlist that you can check it out from. All right, this is going to take... Yes, like I said, we're going to put together several of our conversion factors to do this long dimensional analysis problem. So the first thing that we need to do is we're going to need to take these grams of copper to moles of copper. So you guys have done this a million times. So we're just using the molar mass, oops, that should be a 6 of copper, to go to moles of copper. All right, once we're in moles of copper, we want to convert to moles of electron. So how many moles of electrons do we get with 1 mole of copper? Well, this is why I put this N equals 2 electrons. So you can also think of this from your balanced chemical equation. How many moles of copper do you get from your electrons? So what is the stoichiometric ratio between your electrons and your copper? It is a 2-to-1 ratio. So again, there are a couple of ways to think about this, which is nice because then you can figure out the way that makes the most sense. Okay, so I should put in all of my cancellation. So my grams of copper have canceled. My moles of copper have now canceled. Now I've got moles of electrons. So again, I know at some point I'm going to have to use my amps. So I've got 1.25 amps. So I'm going to have coulombs. And once I get to coulombs, then I'm getting to time. So I'm really, really close to that. But how do I get from moles of electrons to coulombs? By Faraday's constant. So you look at the units there. So this just says moles here, but this should actually be moles of electrons for Faraday's constant. So that's how we're going to go from moles of electrons to coulombs. And then once we're in coulombs, we're going to use our amps to go to seconds. All right, so let's do this. This is Faraday's constant. I want my moles of electrons to cancel. So I'm putting it in like so. 85 coulombs. Okay. So my moles of electrons cancel. Now that I'm in coulombs, what I'm doing here is I'm going to take my 1.25 amps. This might help to see it like this. Is equal to 1.25 coulombs per second. So this is another way to write our 1.25 amps. And now you can see that our coulombs here, they need to cancel. So I'm going to need to flip that. So I've got 1.25 coulombs over 1 second. And now for the final one, it's going to be really easy. But let me show my coulombs have canceled. Now I've got seconds. So there are 60 seconds in 1 minute. And that is what the problem asks us for. It asks us for minutes. So I'm actually going to put this down here. So that is our calculation. So it is all about your units canceling until you get the unit that you want. So you're just stringing together conversion factors in a really, really long dimensional analysis. And this gives us 81.0 minutes. So I know that sometimes these electroplating problems give students trouble because they want like an equation to plug into, but these are almost always going to be just some kind of dimensional analysis problems. So what you really need to think about are the units you have and the units you want to get to. Knowing your amps is a big thing, and recognizing that amps are coulombs per second. That's huge. And when you use Faraday's constant, again, you need to make sure that you really keep track of those units. So in this case, we had our 96,485 in the numerator, but sometimes that's going to need to go in the denominator. All just depends on making sure your units cancel, which is why for any of these problems, please write your units down. Because I'd say for this particular problem, I would say this factor right here probably gets flipped when students don't write their units down. And instead of dividing by your 1.25 there, you're going to multiply, which means you're going to get the wrong answer. So that's why you always write your units down. Okay, so yes, I will show you the last question here. So I really wanted to draw an electrochemical cell, but I'm just kind of running out of time. But I think this is actually, if I'm remembering right, this is an equation from an old AP test or an old AP chemistry exam. So you can see here that they want you to put together a galvanic cell. They have given you both reduction potentials and they have given you the redox equation, which is really helpful. So excuse me, a lot of this is repeating what we did in the first question. We've got to get Ecell for that. So we know how to calculate that Ecell because we did 5 of these just a little while ago. So again, that repetition really helps. So all you need to do is, of course, identify your cathode and your anode and take your E cathode minus your E anode. And that also answers part B. So then you can just write down what happens in part B because you've already identified your cathode and anode because you've used this right here to calculate your E cell. So you had to do that anyway. And then, of course, you sketch your galvanic cell, and then they want you to show the direction of the electron flow. That's going to go from anode to cathode, and the directional flow of the ions on the salt bridge. So your cations will flow from your anode to your cathode, and your anions are going to flow from your cathode back to your anode on the salt bridge. And then again, calculate KEQ. And we were just doing this because once you have your E cell, you can calculate KEQ. And of course, actually, even once you have E cell, you can answer this question, is it thermodynamically favored or not? You just need to know if it's got a positive E cell or not. That is a really, really, really quick overview of this last question. Again, I want to know what do you want to see? What are you doing in class? What are you struggling with? What examples do you need to see more of? You can leave a comment in the chat if you want, or you can leave a comment in the video once it's posted on YouTube. You can message me on Facebook. You can send me an email, but just let me know what you want to see. And I hope you guys are getting ready for that AP exam. I'll see you next week. Bye.